state. Okay, each state is corresponding to the node of the diagram. Okay, and the arc represents one-step transition probability for any pair of states. Okay, but usually we describe non-zero one-step transition probability. Okay, if this probability is zero, then we ignore such one-step transition probability in the diagram. Okay, so when we consider a discrete time Markov chain with transition matrix including many zeros, okay, then instead of constructing a transition matrix, constructing this transition diagram might be much easier than constructing the transition matrix, and very easy to understand that this discrete time Markov chain. Okay. So let's consider an example. Okay. So now in the description, we figured out this transition matrix. Like, so let's say this chain has three different states. Okay, and transition matrix might be 0.5, 0, 0.5, 0.5, 0, 0.5, and 1, 0, 0. Okay. Then let's try to figure out a transition diagram corresponding to this transition matrix. Okay. So how many nodes do we need to construct transition diagram? 3, right? So inside the circle, we can write 1, 2, 3, right? The 1, 2, 3 represents states of the chain. Okay? And then, as I said before, to draw arcs, we are going to consider non-zero one-step transition probabilities. So from state 1, okay, we just consider 2 arcs, right? 1, 2, 1. So this arc with probability 0.5. Okay, and is there any positive one-step transition probability from 1 to 2? No, 0, right? So you don't have to consider such arc. How about 1 to 3? Yes. With probability 0.5. Okay? And then let's consider the cases from state 2. Okay? How about 2 to 1? 0.5. 2 to 2, 0. 2 to 3, 0.5. Okay? How about 3 to 1 with probability 1? 3 to 2, 0. 3 to 3, 0. Okay? So this diagram exactly has the same meaning as this transition matrix. Okay? And much simpler. Okay? So when we try to consider some linear algebra to examine this chain, then you can work on the matrix operations, like finding the unique station distribution and so on. Okay, but sometimes a certain Markov chain I mean, it is much easier to examine this diagram for certain discrete time Markov chains. For example, if the transition matrix has many zeros, okay, much simpler representation to figure out the one-step transition matrix probabilities. Okay. Okay, cut method is another way to figure out stationary distribution. Okay, last class we discussed the definition of stationary distribution and how to find it along with the definition, right? Solving system of linear equations. We have if this state has like k different states, state space has the k different states, then we need to solve k plus 1 linear equations with k unknowns to figure out stationary distribution, right? But when you when you have such diagram, then we have another way to figure out stationary distribution. So we can consider another example. Okay, last one. The last one. Okay, let's consider another example. 1, 2, 3. And transition probability 0.25, 0.25, 0.5. Point 5, 0, 0.5, 0, 1, 0. Okay. Then we can draw this diagram 1 to 1, 0.25. 1 to 2, 0.25. 1 to 3, 0.5, right? And then 0.5, 0, 0.5, and then 3, 2, 2 is 1. Okay. So I believe you can draw this diagram based on the information in this transition matrix. Okay. Now we can consider, flow in represent transition probability into the state times probability in the stationary distribution corresponding to the state, like pi I, and summation of all these flow in might be located in the left hand side, and right hand side flow out. For each arc we can figure out transition probability from the state, right? And then times pi I corresponding to the state. Okay, pi j corresponding to the state of the state. Okay. Let me think about this example first. Okay. So in this case, we can consider three different equations. Okay. First one. Okay. So for state 1, so we can consider all arcs into this this state. Okay. So when we consider state 1, this flow in occurs with this arc and this arc, right? Sorry. Thanks. When we consider this cut method, you need to ignore all the self-feedbacks, okay? Self-feedback, okay? Thank you. So we don't consider this arc, but we can consider flow in from other state, okay? So flow in, consider this arc. So a transition probability from other state, like in this case, state 2, 0.5 times the station probability in the stationary distribution corresponding to the state, the origin of, which is the origin of the arc. In this case, 2. Okay. And we don't have to consider any other arcs for the flow in at state 1. Okay. And this one is the same as flow out. When you consider flow out, as I said before, we don't have to consider any self-feedback arcs. Okay. We don't consider this. But when we consider this state 1, this arc and this arc, they are arcs about flow out at the state 1. Okay? So transition probability from state 1 to 2 is 0.25 times pi 1 plus this arc, for this arc, 0.5 times pi 1. Okay? We can construct such equation for each state. Okay? For state 2. The flow in arcs corresponding to the flow in into the state 2 is this and this, right? Right? So transition probability 1 to 2, 0.25 to 5 pi 1 plus 1 times pi 3. This one represents flow in part of the equation corresponding to the state 2. And the flow out part, we need to consider this arc and this arc, right? So 0.5 pi 2 plus 0.5 pi 2. Okay? And the state 3 for state 3. Flow in part 0.5 times pi 1 plus 0.5 times pi 3 equals 1 times pi 2, pi 3. Okay? And then summation of this pi 1, pi 2, pi 3 might be 1. Okay? Similar to figure out transition stationary distribution with the definition of the stationary distribution, right? But sometimes very useful to figure out stationary distribution of the chain. Okay. So in this case, we can use a similar way. First, we need to solve these equations. Okay. How? We can fix one of the variable as 1. Like, in this case, which one is the best? Pi 1 is 1. I say, Actually, this part is equivalent to the solving pi times p equals pi, right? So let's say when we consider invariant measure first, eta, okay? So if we consider eta 1, this value is corresponding to pi 1, similar to the way we did last class. When we fix this one is 1, okay? Then eta 2 is from this, what do you think? 0.5 eta 2 is 0.75 eta 1, right? So 3/2, right?
So actually the thing in that equation are not p's or etas.
What was that?
That equation in flow in and flow out.
Yes.
They are not p's, they are etas, right?
Not pi, eras. Yeah. First. Okay.
And then you construct the
Yes. We can consider the same way. Okay. We did. So, and then we can transfer to this to pi, like 1/1 plus 3/2 plus 5/4. Pi 2 is 3/2 over 1 plus 3/2 plus 5/4. Pi 3 is 5/4. 1 plus 3/2 plus 5/4. Okay. So this is another way to figure out stationary distribution. Okay. When we consider transition matrix, okay, we need to solve system of linear equations based on pi times p equals pi, right? And all the summation of all the pi I equals 1, right? Instead of solving such system of linear equations, if you have this diagram, okay, then we can first we can figure out easier, simpler representation of the pi times p equals pi. Okay, so sometimes this solving this is much faster than solving the linear equation based on the definition of the stationary distribution. Okay, actually, this is very powerful to figure out stationary distribution of the chain with infinitely many states. Okay, as you know, if a chain has infinitely many states, then I think technically it is impossible to construct transition matrix because we need to consider infinite number of rows and columns, right? But in that case, I'm going to show this case like called random walk and reflected random walk. I'm going to talk about this later. But in that case, as long as we can figure out the transition matrix and we can figure out the property of the chains, then based on the cut method, we can calculate the stationary distribution corresponding to the chain. Okay, so this is another way to figure out stationary distribution. Okay, I'd like to introduce more terminologies now. So far we discussed about how to calculate stationary distribution of the chain. But before we try to solve try to figure out stationary distribution of the chain, sometimes we need to firstly figure out whether such stationary distribution exists or not, and this stationary distribution is unique or not. Very important. After that, you can calculate long-run average values. Actually, calculating long-run average value might be ultimate goal of analyzing this processes. But before we try to calculate such measures, okay, we need to know whether this chain has the unique stationary distribution or not, right? To understand such subject, we need to introduce new terminologies. First one is irreducibility. I think most of you haven't heard about these words, right? Right? No, haven't. Yes. So irreducibility. Before we discuss about irreducibility, we need to understand accessible and communicate the meaning of these words. Okay. So when you try to analyze discrete time Markov chain, okay, let's say this large X represent a discrete time Markov chain on a certain state space S with the transition matrix large P. Okay, this for a certain state I and J. Okay, this state I is accessible to state J if there exists any non-zero probability transition probability from I to J with finite n. Okay, not just one-step transition probability, but as long as we can move the state I to J with positive probability and the finite step, then we call this I is accessible to J. Okay, let's consider the original example. I mean, what was that again? I think point 5, 1, 2, 3 to 1, 1.5, 0.5, 0.5. Okay, this one. Okay. So the question is the state 1 accessible to state 3? Yes or no? Yes. With probability 0.5, with just one step, it is possible, right? How about 1 to 2 to 1? Yes. 2 to 3? Yes. 3 to 1? Yes. 1 to 3? Yes. Right? How about 2 to 1? No. It is, no, sorry. 1 to 2? No. It is impossible. If you consider many steps, even though you consider many steps, but it's not possible to consider the transition from 1 to 2 or 3 to 2. So we call this 1 is not accessible to 2, and 3 is not accessible to state 2. Okay? Okay. How about this case? Like 1, 2, 3, 4. Okay, 1 to 2, 0.5, 0.5, 0.25, 0.5, 0.25. Sorry. Yes. 0.5 like 1. Okay, in this case, when you consider this, let's think about direction from 4 to 2. The other way around first. 2 to 4. Yes, right? Let's consider different. Okay, we can erase this. How about this case? 2 to 5, is it possible? Accessible from 2 to 4? Yes, right? With 2 steps, right? As long as with finite step and the positive transition probability, then we can say that this state is accessible to another state. Okay? Okay, but how about 4 to 1, 4 to 2, 4 to 3? Not accessible, right? Not accessible. There is no positive probability from 4 to any other state with finite steps. Okay?
It doesn't matter how many steps, right? So as you find more.
As long as we can figure out non-zero probability with finite steps, that's fine. Okay? So you can understand what accessible is, right? And communicate. So in this case, for 2 states, we can consider accessibility from this state to this state and this state to this state. Okay? So if I is accessible to J and J is accessible to I, then these two states can communicate. Okay? IJ says to communicate each other if I is accessible to J and J is accessible to I. So how about in this case we can consider 1 and 3. Yes. State 1 is accessible to 3 and state 3 is accessible to 1, right? How about 1 to 2, 1 and 2? They are there's no way to communicate 1 and 2. Okay? So communicate is about the relationship between 2 states. Okay? And accessible is also about 2 states, right? And let's consider whole chain, not just a pair of the states. Okay? When we consider any pair of states, if this all pair of states can communicate each other, then we call this chain irreducible. Okay? So irreducibility is the characteristic of the chain. Okay? Accessible or communicate these words is about certain 2 states. Right? But when we consider any pair of states and they can communicate each other, when we consider any pair of states, then whole chain is called a irreducible chain, discrete time Markov chain. Okay? What do you think? This? No, because 2 and 3, there's no way to communicate. Okay? 2, 1, right? Similar. In this case, no. But how about this? 4 to 1, 1. What do you think? Irreducible or not? Irreducible, right? So let's think about accessibility from 4 to 3. Even though we consider this way with 3 steps and 0.75 times 0.5 times 1 probability, non-zero probability, we can access from 4 to 3. Okay, so you can figure out from the diagram, you can figure out accessibility from a certain state to another state. Okay, so this is the power of transition diagram. Based on the diagram, you can figure out it. Okay, and if this chain is not irreducible, okay, not irreducible, then we call this reducible. And we are going to talk about this the end of the chapter. Okay. So recurrence is another concept. Recurrence is very hard to understand at the first time. So we need to introduce new notation tau to understand recurrence. So recurrence and transience, this is about characteristic of each state, not pair of the states. Okay, in this case, accessibility or communicate each other, these things are about the pair of the states, right? But recurrence, transience, this is about the characteristic of each state. So technically, you can figure out this characteristic for each state of the chain. Okay. And tau I represent, if we start with the state I, and then how many times we need to evolve the chain to come back this state. Okay, this number of steps represent tau I. Okay, for example, in this case, you can so if I is 1, okay, probability of tau 1 equals 1. Just come back with the one step. Might be 0.5. Just with one step, we can come back. Right? 0.5. Can you come back to the state 1 with 2 steps? Yes. How? This and this. Right? Any other way to come back to the state 1 with 2 steps? No. So probably that tau 1 equals 2 with 2 steps equals 0.5 times 1. Okay? Huh? 1 to 1. Transition from 1 to state 1 with 2 steps. Any other? Oh, good point. No, sorry. This is about the first time. So when you leave, okay, then when is the first time to come back? So 1 means we come back. When you consider this twice, that means first time to come back might be this. Okay? Okay? So do you understand what's the meaning of the tau I? Okay? When you start with I, then how many times to come back? Firstly, come back to the state I. This step represents I. Okay? Actually, this one is random variable. Tau I is random variable, not deterministic number. Okay? Because it depends on the transition probabilities. So based on the definition of recurrence and the transient, okay, transient is 0.5 times 1. Yes. Why? Because we can consider these two arcs to come back to, from 1 to 1 with just 2 steps. This is the only way. Okay? Okay. So recurrence is when you consider the state I. Okay, if we start with the state I, as I said before, this recurrence and the transience is characteristic of each state. So when you consider a certain state like state I, okay, that means we start with I, and then if probability that this tau I is less than infinite, we can come back with the finite step with probability 1, then we call this state this state is recurrent. Okay, this state is recurrent. And this positive recurrence is a stronger condition than recurrence. Okay, if we consider expectation of tau I, this expectation of tau I is less than infinite, finite, then we call this state positive recurrence state. And state I is not recurrent, then we call this transient state. So very, I think most of you are confused of the concept, right? Right? I'd like to introduce how to determine recurrence or positive recurrence or transient of the state later. Okay, we have another way to figure out it. Okay, but the thing is, this recurrence and transience. So each state has one of this property: recurrence of transience. Positive recurrence is if positive recurrence is a smaller concept than the recurrence, to include it in the recurrence. Okay. So largely we can determine whether this state is recurrence or not. Or not means transient. Okay. And for a chain, for Markov chain, if all the states are positive recurrence, then the chain is called a positive recurrent chain. If all the states are recurrent, then this chain is called a recurrent chain. Okay? So this recurrence and transience, it can be a characteristic of the chain. As long as all the states is satisfied with the recurrence concept, then the chain is recurrence. Any of them, one of the state is transient, then the chain is transient. Okay. So I'd like to introduce how to determine whether each state is. We can use the definition, but you need to know many mathematical techniques to figure out whether the state is recurrence or not, positive recurrence or not, based on the definition. But we have another way, so I'm going to introduce it. This is very important concept. So, if the chain is irreducible, Okay. And this is very important concept. Before we consider this, if chain is irreducible, okay, one of the state is recurrent, then the chain is recurrent. This is under the assumption that chain is irreducible. Okay. So firstly, you can figure out whether the chain is irreducible or not. If yes, then as long as you can figure out the recurrence of the state, one of the state, then this characteristic can be shared with the whole chain. Transience is also. One of the state is transient, then the chain is the transient state, transient. And very important concept is here. So if the chain is irreducible with the finite state, okay, finite state, mainly we are going to consider such cases, okay, with finite states, right? 4 states, 3 states, and so on. As long as the chain is irreducible with the finite state, then the chain is positive recurrent. You don't have to prove anything. Okay, what do you think about this chain? Irreducible? No. Reducible, right? So we don't use any concept about determining positive recurrence of the chain. Okay. But in this case, irreducible, right? And the chain is chain has the finite state. So even though we didn't prove anything, or we use any concept of the definition regarding recurrence or not, we can see that this chain is positive recurrence. This state space includes finite state. I mean, this S includes finite number of states. Mainly, we are considering such cases. But when we consider random works, state space is defined on negative infinite to infinite. Then we need to consider another way to figure out it. But as long as the state space is finite, I mean including the finite number of states, then just you can figure out irreducibility of the chain, and then determine the positive recurrence of the chain. And actually, why do we need to such subjects? I mean, irreducibility, positive recurrence, or transient. Actually, we would like to determine existence of the unique stationary distribution. Okay. The thing is, based on the definition of stationary distribution, like solving, I mean, this definition is about linear equations, right? So when you solve this linear equation, and then you can figure out the unique solution, then you don't have to consider such subjects. Okay? But before you try to solve this, try to figure out stationary distribution. Okay? Sometimes we need to determine whether this chain has the unique stationary distribution or not. Then first you need to figure out whether the chain is irreducible or not. Okay, and then second, whether this chain is positively recurrent or not. Okay, if the chain is irreducible as well as positively recurrent, then you can figure out the unique stationary distribution. Okay, and one more concept. Sometimes you need to figure out whether this chain is positively recurrent or not to calculate some probability or some possibility. Okay. Sometimes finding unique stationary distribution is easier than figure out whether the chain is positively recurrent or not. In that case, as long as you can figure out the chain is irreducible, and when you figure out the unique stationary distribution, then we can conclude that the chain is positively recurrent. Okay, because these two concepts are about the if and only if, has the if and only if relationship.